Hello, and welcome back to the course on thermodynamics. We are still on Unit 3 of this course, which is all about the first law of thermodynamics. So let us first review some concepts that we have discussed in the first previous lessons. We have discussed about the first law of thermodynamics, which is all about change in internal energy of a thermodynamic system, and it's just equal to the heat absorbed by the system minus the work done by the system. So it's basically a conservation of energy principle. So in terms of, in the case of an ideal gas, the change in internal energy is just dependent on the change in temperature. But again, this is just only true for an ideal gas. So in this lesson, we will be now talking about the different kinds of thermodynamic processes and how is heat and work and the change in internal energy involved in these different types of thermodynamic processes. So the first thermodynamic process that we will discuss is an adiabatic process. So in an adiabatic process, no heat is transferred uh, into or out of the system. So meaning Q is equal to 0. In that case, the first law of thermodynamics becomes delta U is equal to just negative W. So Q is equal to 0. So an adiabatic process can undergo expansion, wherein there will be a decrease in temperature, or compression, there will be an increase in temperature. So for instance, in the example on the cork on a champagne. So inside the champagne, there is a pressurized gas. And this pressurized gas, high pressure gas, will actually expand rapidly when you open the champagne. And there's no time for the gas to exchange heat with their surroundings. So meaning there's no time for heat transfer, for the gas to absorb heat, or for the gas to release heat. So it's an adiabatic expansion in this case. And the gas, instead, the gas just uh, expands. And when the gas expands, so the work done is positive. Meaning, if the work done is positive because the gas is expanding, the change in internal energy is negative work. So if the work is positive, then the change in internal energy is negative. So you have a negative change in internal energy. And a negative change in internal energy means a decrease in temperature, since internal energy depends loosely on temperature. So in that case, the temperature of the gas here drops, and it forms a water vapor cloud, a cold cloud of gas or foam in the case of a champagne. Actually, this also happens inside a soda can. If you open a soda can or a soda bottle and you shake it before you open it, then that's what happens. It's an adiabatic expansion. So the second process is an isochloric process. It's a constant volume process. So meaning the change in volume is zero, meaning the work done by the system is zero because there's no change in volume. So in that case, the first law of thermodynamics just becomes delta U is equal to Q. So the change in internal energy is just equal to the heat absorbed by your system. So if the heat absorbed by your system is this one, NCV delta T, where CV is the heat capacity at constant volume. So in this case, actually we have presented this equation before in the unit 1 when we discussed about the specific heat. And this is the heat absorbed by N moles of gases, ideal gas, when it changes its temperature, delta T. So in this case, in an isochloric process, there's no expansion, there's no compression. So the system is not compressed or expanded because it's a constant volume process. So example of that is pressure cooking. So in pressure cooking, it's an isochloric process. The volume is constant, but the pressure and the temperature inside the system changes. The next process, this is actually the third type of thermodynamic process, is an isobaric process or a constant pressure process. So in a constant pressure process, the heat and the work is not necessarily zero. Again, in an adiabatic process, the heat is zero. In an isochoric process, the work is zero. But in an isobaric process, there's no zero terms. So that's just your in this case, the heat absorbed by your system is equal to this one, NC delta T, where your C now, the heat capacity, is now heat capacity at constant pressure. So isobaric processes can undergo expansion and compression. So when it expands, it decreases its temperature. When it compresses, it increases its temperature. So most cooking involves isobaric processes because we're just cooking at atmospheric pressure. So the pressure above your frying pan or your cooking pot is just the same as the pressure inside the pot or inside your soup or inside or the food that you're cooking. So it's an isobaric process. The last process, the fourth one, is what we call isothermal process. From the word thermal, it refers to temperature. And as you have guessed it, in the first process that I have mentioned, iso means constant. So isochoric means constant volume. Iso means constant, choric means volume. Isobaric means iso constant, baric means pressure. And isothermal means iso constant, thermal is temperature. So isothermal means constant temperature process. So in this case, the change in temperature is zero because it's a constant temperature process. Generally, since it's a constant temperature process, there are no zero terms in the first law of thermodynamics. The heat and the work is not necessarily zero again. So it can undergo expansion and compression. So example of that is the phase change process. So if you have a melting, freezing, or evaporation or condensation process, it happens only at a certain temperature. So phase changes only happens at one temperature, the boiling points or the melting points. So those are example of where isothermal processes can occur. For an ideal gas, since the change in internal energy for an ideal gas depends only on the change in temperature, and since in an isothermal process the change in temperature is zero, then for an ideal gas the change in temperature is zero. So if the change in temperature, sorry, the change in internal energy is zero. So if the change in internal energy is zero, if this is zero, this means that the Q, the heat absorbed by the body, is just equal to the work done by the body. And in this case, it's equal to nRT. T is the isothermal temperature. Ln of the volume 2 over volume number 1, if there is a change in volume. Obviously, there will be a change in volume in an isothermal process. Okay, so this is the PVT diagram for ideal gases. So we'll now focus our discussion on ideal gases. So the lines or the curves that you see here, the blue curves that you see in this diagram, is what we call an isotherm, a constant temperature na path. So all of these blue lines here, one blue line corresponds to one temperature. Another blue curve here corresponds to another temperature. So it's a PVT diagram. It now has pressure, volume, and temperature states. So path A21 from point A or state A to state 1, that path or that process is what we call an adiabatic process. And in this case, it's adiabatic expansion because the volume increases. And you will notice that point A is on one isotherm, this isotherm, and point 1 is on another isotherm, meaning the temperature changes in this case. So in an adiabatic expansion, you will notice that the pressure decreases, the volume increases, the temperature will also increase. So this is increasing temperature. So the isotherms here from the top to the bottom, this is increasing temperature. So from point A to point 1, from state A to point 1, the temperature is increasing. So in an adiabatic process, all of the three state variables are changing. Now, the path A to 2 is what we call an isocoric process, constant volume. So there's no expansion or compression happening here because the volume is constant. Instead, the pressure decreases in this case, and the temperature increases. So from the temperature is from this isotherm here, and it now goes to this isotherm here. So the temperature increases, the pressure decreases. Path A to 3. A to 3 is an isobaric process, constant pressure process. So from point A, it's actually an isobaric expansion because the volume is increasing. Again, compression is in the opposite direction. Compression is decrease in volume. So this is an increase in volume from VA to this volume here, say V3. And you will also notice that the temperature changes. The volume and the temperature changes in an isobaric expansion. So the pressure is constant, but the volume changes and the temperature also changes. In this case, the temperature actually decreases. Sorry, I think I have made a mistake, and instead I have mentioned, sorry, baliktad ang ako ang temperature. So this is the increasing temperature there. So this isotherm here, this last blue curved line is the lowest temperature, and this isotherm here, this blue curved line at the bottom, is the highest temperature. So temperature is increasing in an isobaric expansion, and in an adiabatic expansion, the temperature is decreasing. So the pressure decreases, temperature decreases. Okay. So the last path, path A to 4, this is an isothermal expansion. If you will notice, path A to 4 only happens in a single isotherm, in a single blue line curve. So meaning the temperature at point A is just equal to the temperature at point number 4. So that's an isothermal expansion in this case. So the temperature is just the same, but the pressure and volume changes. So the pressure actually in this case in an isothermal expansion drops, the pressure decreases, the volume increases. So in an adiabatic process, again, I would like to emphasize that all of the state variables, pressure, volume, and temperature changes in an adiabatic process. In an isocoric process, volume is constant. Isobaric process, pressure is constant. Isothermal process, temperature is constant. Okay, let's now have an example. So isothermal compression of an ideal gas. So during an isothermal compression of an ideal gas, 335 joules of heat must be removed. So remove means negative heat from the gas to maintain the constant temperature, since this is an isothermal expansion. So how much work is done by the gas during the process? So in this case, isothermal expansion of an ideal gas, since this is an ideal gas, the change in temperature, the change in internal energy is just equal to 0, since there's a 0 change in temperature. Meaning the heat, in this case, the heat removed from the gas must be equal to the work done on the gas. So this is work done on the gas because this is compression. You're working or transferring, you're working on the gas. You're transferring energy to the gas to compress it. So of course, it will just be equal to the heat removed. So the heat removed from the system is negative 355 joules. So the work done must also be equal to negative 355 joules. Okay. So again, work is not done by the gas, but work is done on the gas. The negative sign in the work here implies that work is not done by the gas, work is done on the gas. So this is a picture of an isothermal compression of ideal gas. So the one doing the work is actually the surroundings of the gas, in this case the piston, and this will uh, uh, increase the pressure of the gas while decreasing its volume. But the temperature remains the same because the gas is releasing heat to the surroundings. So that's how it maintains its temperature. So it releases heat to maintain an isothermal temperature. Okay, example 2. Adiabatic expansion of ideal gas. So during an adiabatic expansion of a mole, so we have 1 mole of ideal monoatomic gas, the temperature decreases by 50 Kelvin. So this is the change in temperature. 50 Kelvin here is the change in temperature. So how much work is done by the gas during this process? So in an adiabatic expansion, there's no heat involved. So the change in internal energy is just negative work. So we are just trying to solve for the work. So the work is just, therefore, the work is just the negative change in internal energy. And since this is an ideal gas, for ideal gas, the change in internal energy during an adiabatic expansion is just equal to the NCV delta T. So for an ideal monatomic gas, the heat capacity at constant volume is 3 halves R. That's approximately 12.47 joules per mole Kelvin. So we substitute all of that. We have to be careful here. The word, this again, I mentioned earlier that 50 Kelvin is the change in temperature. And this is a decrease. A decrease means a negative change. So you have to put the negative sign here. So the change in temperature is negative 50 Kelvin because it decreases by 50 Kelvin. So that means the final minus initial temperature is equal to negative 50 Kelvin. There's a decrease, a negative change or a decrease. So the work done by the gas in this process is positive. So the gas is the one doing the work because the gas here is adiabatically expanding. It's actually the one lifting the piston up in this picture. So the work done by the gas is positive, meaning the gas is the one doing the work. Okay, so make sure to take note of all the signs of the work and heat when you are dealing with problems in thermodynamics. Okay, last example. Let's now compare the different thermodynamic processes. So we have here a PV diagram. And we see 4 states. State A, state B, state C, state D. So a series of thermodynamic processes is shown in the PV diagram. So in this PV diagram, in the process A to B, so in the process A to B, the process A to B is an isochoric process. So in this process, A to B, 150 joules of heat is added to the system. So that's positive heat because that's added to the system. And in the process B to D, 600 joules of heat is also added to the system. So find the internal energy change of the system in the process A to B, the internal energy change in the process A to B to D, and the total heat added in the process A to C to D. So let's first start with the first problem, letter A. The internal energy change of the system in the process A to B. So in the process A to B, the change in internal energy is just the heat absorbed by the system from A to B minus the work done in A to B. So since this is an isochoric process, meaning there's no change in volume, so the work here is 0. So 0 work done. So the change in internal energy from A to B is just equal to the heat absorbed by the system, 150 joules. That is given in the problem. Okay. Letter B, the internal energy change in the process A to B to D. So in the process A to B to D, the internal energy change is just the addition of the change in internal energy from A to B plus the change in internal energy from B to D. So we already know this one in the first problem in letter A. So we only need to use this one, or to solve for this one, the change in internal energy from B to D. So from change in internal energy from B to D, this is the heat absorbed in the process B to D, which is given 600 joules of heat, minus the work done in B to D. So the work done in B to D, so again, this is already given, but the work done is just the change in volume times the pressure in the process B to D. In the process B to D, This occurs at this pressure here, 8 times 10 to the 4 pascals. And the final volume is the volume at point D, which is 5 times 10 to the negative 3 meter cubed. The initial volume is at point D, which is 2 times 10 to the negative 3 meters cubed. So you substitute all of those values, and you will get a value of 240 joules for the work done. So I can now solve for the change in internal energy from B to D. So 600 joules minus 240 joules, and that will give me 360 joules. So 360 joules is the change in internal energy from B to D. I already solved this one, the change in internal energy from A to B in the previous letter. So therefore, that's 150 joules. So therefore, the change in internal energy in the process A to B to D is 510 joules. So that one. So again, if you're solving for the internal energy from one state to another state, actually it doesn't matter on the path, but you just have to add the change in internal energy for each sub processes. So in the process A to B to D, the total change in internal energy from A to D is just the change in internal energy from A to B plus the change in internal energy from B to D. Okay, that's for letter B. Now, letter C, the total heat added in the process A to C to D. So it's just the heat absorbed in the process A to C to D minus the work done in the process A to C to D. But this is just equal, the change in internal energy from A to C to D is just equal to the change in internal energy from A to B to D. Why? Because again, the change in internal energy doesn't depend on the path. Only the work and heat depend on the path. So the change in internal energy from A to D, it doesn't matter if you go from A to B to D or A to C to D, the change in internal energy, if the initial state is A and the final state is D, will always be the same. So meaning, I now have solved the change in internal energy from A to C to D. It's just equivalent to what we have obtained in letter B. Okay, so so from here, so if you focus on this term here, since in letter C, we're only asked to find the total heat added in the process A to C to D. So this term here, total heat added from A to C to D. So this Q is the unknown in the problem. So working on this equation, we transpose this term here on the other side of the equation, and it becomes positive. So we already know this. So I just, instead of using the subscript A to C to D or A to B to D, I just place A to D. It doesn't matter again. The change in internal energy doesn't matter, doesn't depend on the path. So A to D. So we have already solved this in the previous problem in letter B. So all we need now to solve is the work from A to C to D in order to solve the heat. This is the unknown in the problem in letter C. So this is if we can solve this, we can solve this problem. Now, the work from A to C to D, so this is from A to C. A to C is an isobaric process, so you can solve for the work here. C to D is an isocoric process, constant volume. Constant volume means there's no work, meaning the work from A to C to D is just equal to the work from A to C, because the work from C to D is 0. This is an isocoric process, constant volume. If there's no change in volume, there's no work done. Okay, so all we need to do is to solve for the work done from A to C. So the work done here is A to C occurs at a pressure of 3 times 10 to the 4 pascals. And the change in volume is from 2 to 5 times 10 to the negative 3 meter cube. So you substitute all those values. So the pressure is at point A, 3 times 10 to the 4. And you get a final value or a final unit of joules. So work from A to C is 240 joules, and this represents the work from A to C to D, because the work from C to D is 0. So we can now solve for the heat added in the process A to C to D. So it's just a change in internal energy, which is 510 joules. We have solved this in letter B. Plus, so sorry, I made an error. The work done from A to C is just 90 joules. And this represents the work done from A to C to D. So therefore, the heat absorbed by the system is just the change in internal energy from A to D, which we have obtained in letter B, 510 joules, plus the work done from A to C to D, which is 90 joules, and we get the heat absorbed in the process A to C to D to be equal to 600 joules. So take note, it's very different. In the process A to B to D, the total heat absorbed is actually 150 plus 600. That's actually 750 joules from A to B to D. But in A to C to D, the heat absorbed is only 600 joules. And the work also differs. The work done from A to B to D is also different from the work done from A to C to D, because both the heat and the work depend on the path. But the change in internal energy is always 510 joules from A to D. No matter what path you take, A to B to D, this one, or A to C to D, this one, the work done, the change in internal energy of the system will always be 510 joules. Okay, so that is it for this lesson. So we now have a deeper understanding about the first law of thermodynamics and on the different types of thermodynamic processes. So we will end this unit with two more lessons on heat capacities of ideal gases, and we will, in the last lesson, we will focus on the adiabatic process for an ideal gas, because in the adiabatic process, the pressure, the volume, and temperature of the system doesn't necessarily change. So I will see you again in the next lesson.